Hello everyone, welcome to lecture 13, Man-in-the-Middle Attacks. This will probably be one of two videos. So, man-in-the-middle attacks can occur in many situations, from network authentication to web proxies and even personal interactions like in a phone call or actually in person too. So one example is Nokia. Nokia had this browser named Nokia Express, and what it would do um, would this app would decrypt and compress HTTPS traffic and route your traffic if you're using your phone, Nokia phone, through Nokia servers for supposedly for speed and lower data usage, so that because they could compress it just right. However, this process did give the company access to clear text versions of everything you were doing, so things like usernames you might have entered, or passwords, credit cards, things like that, and that was a big red flag. Although they were not shown to have any malevolent intent, it was definitely a potential problem. So this was something the users didn't know, and that was the big problem. Another case of a man-in-the-middle attack was in 2011 in Iran. Someone using Google Chrome noticed that there was a warning about a Google site, and it turned out that browsers like Chrome would hard code fingerprints for some Google sites. So there's Google sites all around the world, and so um, just to avoid problems like man-in-the-middle attacks, they would actually hardwire the IP addresses and things like that, and also the keys for some sites. And so, if there was ever a problem with encryption keys, things like that, the browser could detect it. So it turned out what was happening was the user was visiting a site that was most likely set up by, we don't know, but probably the Iranian government, and that site was pretending to be Google but was not. It was actually set up by somebody else. And so you might ask the question, how can someone pretend to be Google? Well, in this case, it turned out that Dutch certificate authority issued fraudulent certificates. So that's how this um, site was pretending to be Google. So you would do your business, you would like search for something, and what would happen is the site would log all the searches, and it would actually send those searches onto a real Google site. And then when that Google site comes back with when the real site comes back with the results, this fake site would present those results as if it was, as if you were getting it from Google. And so why would someone do this kind of man-in-the-middle attack, pretend to be someone else? Basically to snoop on people, to figure out what people are doing. Okay. And it turns out a couple of years later, um, there were slides found in a GCHQ and joint NSA presentation on what was called the Flying Pig program, and it basically showed how to impersonate sites like Google using fake security certificates. And so basically it was doing just exactly what the Iranians were doing. Someone would try to um, um, access Google. Instead, a router would route all of this stuff to a man in the middle, which was like um, the NSA or GCHQ combine their site, and then they would figure out what people were searching for, and then forward those search requests into the actual Google site. And the idea is you could snoop on people once again, just like with the Iranian site. So how does someone go about impersonating a website? Turns out it's not that hard. The key is you have to get a fraudulent certificate. That's one way of doing it. So you have to go to a certificate authority. There's more than 1,000 certificate authorities, and they're spread out all over the world, 50 countries. And you'll see this time and time again with things on the internet. There's just so many of them in very different places. So you can find a certificate authority that will actually sell you one. You can bribe someone. They're not supposed to do this, but maybe you can find one that'll sell you one. Or just break into one and steal one, or break into a router near a certificate authority and read all of the traffic and figure out how to break in, and, or figure out how much, how you can actually get a certificate authority just by reading their traffic. So there's many ways to do this, and there's so many of them that it's bound to happen. And actually, it looked like it did happen at least in a few cases. Okay, so we'll see more situations like that, but first, let's take a look at key exchange. So remember the steps for getting one symmetric key that you can share to encrypt and decrypt data. So remember that someone, let's say Amy, says to Bill, they want to end up sharing a symmetric key, but they start out with the public and private keys, basically getting public keys. So Amy tells Bill, give me your public key. Bill says, here's my public key, Amy. And then Amy uses that to encrypt a symmetric key and send it to Bill. And then Bill can decrypt because he has his private key. And then from that point on, both sides, Amy and Bill, know that what the symmetric key and all the exchanges between them can be encrypted using that symmetric key. Okay, so that's the basic idea to a key exchange now. That's what web browsers do, and a lot of other protocols. So what's wrong with that? Well, it turns out a man in the middle can snoop and listen to traffic and intercept this traffic. And so we would say that there's Amy, there's Bill, and then there's the malevolent person, or Mallory, who is able to intercept the conversation between Amy and Bill and get Bill's public key. So in that process, so what happens is Amy says, Bill, give me your public key, and Mallory intercepts that, doesn't send that message, but instead sends a message where the reply will go to Mallory. And then when Bill answers with to what he thinks is Amy, or the person he thinks is Amy, it turns out he sends his public key to Amy. Actually, it turns it out he sends it to Mallory. That's not a big deal because Mallory doesn't have Bill's private key. He only has the public key, and that's okay. But the problem is then Mallory will send send not Bill's public key, but Mallory's own public key to Amy. And then from that point on, Amy will use Mallory's public key thinking it is Bill's. So this man in the middle, Mallory, has pretended to be Bill to Amy and Amy to Bill. That's the whole idea. And then from that point on, when Amy sends a symmetric key encrypted using Mallory's public key, Mallory is able to decrypt it and then encrypt it using encrypted using Bill's public key and then send it on to Bill. So now we have a point where Amy and Bill think they're talking to each other, but they're really both going through this intermediary that is Mallory. And so Mallory can pretend to be both Amy and Bob to the other person, Amy and Bill. Okay. So these kinds of problems crop up in many situations, and one of them is in domain name services. So domain name services, like when you say, for example, access a new site, like let's say you've never accessed liverpool.ac.uk. It's just the name of a university in the United Kingdom. Let's say you've never accessed it. So if you've never accessed it, your computer will need its IP address. Let's say if you're browsing the web or something, and it'll ask, let's say, a local name server, some name server that's close to you, maybe not on the same subnet, maybe it's outside your subnet, and then the whole idea is that this domain name server will take this liverpool.ac.uk fully qualified domain name and convert it to an IP address and send that to you. So try that out. It'll take, you can actually intercept the traffic between you and the domain name server and watch it in Wireshark or something like that, and see how this happens. So we've summarized that in this diagram where the user says, please convert www.microsoft.com. And this domain server, which can be maybe in your network, maybe most likely outside your local area network, will respond with an IP address saying the IP address for www.microsoft.com is 207.46.197.32. Okay, so as of a couple of years ago, this is almost 3 years ago, there were 325 million domain names. And it's just not feasible to store all these domain names and IP addresses locally, or even in a single server. So in the very beginning of the internet, you actually did store a whole bunch of IP addresses in your local machine. You cannot do that anymore. We cannot even have a single server save it, because actually fully qualified domain names, they change their IP addresses all the time. They can. They don't have to, but they can. And so you need something a little bit more dynamic. And so it turns out the domain name system is a global system, and then there are 13 logical root name servers. So that's a.rootservers.net, b.rootservers.net, and so on up to m.rootservers.net. And so these are spread out around the world. If they don't have the IP address that you're looking for, let's say www.microsoft.com, they will refer you first to a top-level domain name server for the top level of the name, like .com in Microsoft.com, or .uk for the liverpool.ac.uk part. Okay, and then these things, these top-level domain servers will say, okay, I don't know what Microsoft.com is, but you can ask the .com name server, and so on, and then it'll filter down all the way to the lowest level. Eventually, it'll reach Microsoft.com or Liverpool.ac.uk. So that's recursively resolving the domain names. A top-level domain name will know of the appropriate name server for some address like Microsoft.com or Google.com or ac.uk, and then eventually some server is going to send all of that, the information that you're looking for, to you. So our system will query these name servers one after another, and eventually the appropriate one is found. So there's a whole bunch of servers potentially involved in looking for just one domain name. So a man-in-the-middle DNS attack can intercept these servers' responses, which contain IP addresses, and then instead fake out you, the person who's searching for, let's say, Microsoft.com, and just respond with the IP address of some machine that's probably working with the attacker. So this is the attacker, this is you, the innocent user, and this is some service that you're using, in this case the DNS service. You ask for www.microsoft.com, and then it responds. Well, before it gets a chance to respond, the evil man in the middle will respond with the IP address of a server, and the DNS server might also respond, but by the time it gets there, it's probably going to be received too late and it'll be ignored. Okay, and then once you get that fake address 7.0.1.1, let's say, you, the user, will send all your data to 7.0.1.1, thinking that it's Microsoft. You might be logging into your account or whatnot. Then the attacker can now see all of the messages that you are sending it, and then maybe the attacker can maybe grab your credentials by forwarding your username and then storing your password and also sending it on to Microsoft, and then maybe pretending that it didn't work, or maybe just getting all the messages from the Microsoft server and displaying it to you. But either way, it's now able to see, or the server at 7.0.1.1 is able to see all your traffic going to some site that you trust, let's say. Okay, so another instance of a man-in-the-middle attack. What kind of countermeasures can you have? So there is a security addition to DNS. So the domain name system security extensions that provides authentication for origins. So it uses digital signatures and it uses encryption, all this encryption schemes that we've talked about, um, certificates, signatures for DNS records using public key cryptography. So same kind of thing we've been talking about in the past. And so the correct DNS key record is authenticated using what's called a chain of trust. And this essentially prevents man-in-the-middle attacks from directing a client to malicious IP address. There are newer approaches to DNSSEC that involve blockchains too, so that you can always be checking that just chain of trust. Okay. In general, what are countermeasures for man-in-the-middle attacks? You can prevent these things basically by using authentication. And this usually uses schemes like public keys, schemes like TLS. And so that's what's used in web traffic. So these things work. It's very hard to pretend to be a website that you're not. It's still possible, but it's becoming less and less feasible. So man-in-the-middle attacks are detected, although sometimes after the fact, using tamper detection. So after some attack has occurred, you might detect it and then maybe take action. So things like discrepancies in response times, like let's say you're getting a response way too fast for it to be actual response, then, or if there's abnormal latencies, very long latencies, then it might suggest that your data is being intercepted and then fake data or modified data is being passed on to you. So and also you can use forensic data like captured network data, and that can reveal attacks that took place in the past. So once you gather a lot of data, you do have to gather a bunch of data, timing data, source and destination, all those things, and then you can reconstruct what happened. Okay.